Hello, everyone, and welcome back to our series on knowledge tracing. Today, we're going to demystify one of the most fundamental and widely used models in machine learning, logistic regression, or LR. We'll break down exactly how it works, from its core concepts to a step-by-step calculation. Let's dive in. So, what makes LR different from models like IRT? Imagine a teacher trying to predict if a student will get the next question right. The IRT model is like a simple ruler, measuring a single ability score. But LR is more like a chef. The teacher gathers many ingredients, like past performance, time spent, and recent activity, and combines them with specific weights to create a final dish, the probability of success. It's a much richer and more nuanced approach. The beauty of logistic regression is its simplicity. It all boils down to two fundamental steps. First, we perform a linear combination, or a weighted sum, of all the student's features to get a value we call z. Think of this as calculating a student's total score, or risk score, based on their grades, attendance, and other inputs. Second, we take this score z and pass it through a special function called the sigmoid or logistic function. This function acts like an S-shaped curve. It's the crucial step that transforms our unbounded z-score into a value between 0 and 1, which we interpret as a probability of success or failure. That's it. 2 steps to turn raw data into actionable probabilities. Let's break down the key components. First, the features, X. These are just the data we collect about a student, like how many questions they've answered correctly, or if they got the last one right. Second, the weights, W. These are the secret sauce of the model. The algorithm learns how important each feature is. For example, if the weight for last question correct is high, the model has learned that recent performance is a strong predictor of future success. We also have the bias term, B, which is a baseline probability when all features are 0. The linear predictor, Z, is simply the total score we get from the weighted sum. Finally, we have the sigmoid curve, shown here. Notice how it takes any number on the x-axis and squashes it into a value between 0 and 1 on the y-axis. A high positive z-score means a high probability of success, while a negative z-score means a low probability. All right, let's put this into practice with our student, Xiao Ming. Here are his features. He's answered 3 questions correctly out of 5, got the last one right, and spent little time on it. Here are the weights and bias that the model has learned from historical data. Our goal is to calculate the exact probability that Xiao Ming will get the next question right. Step 1 is to calculate the linear predictor z. We simply plug in the numbers. 0.4 times 3 is 1.2, 0.1 times 5 is 0.5, and so on. Adding them all up gives us 2.6. We then subtract the bias of 1.2, which gives us a final z-score of 1.4. This positive score suggests a good chance of success. Now for step 2, applying the sigmoid function. We take our z-score of 1.4, negate it to get minus 1.4, and raise Euler's number e to that power. This gives us approximately 0.2466. Plugging this into the formula, we get 1 divided by 1.2466, which is roughly 0.802. So, the model predicts an 80.2% probability that Xiao Ming will get the next question right. You might be wondering, how do we find the optimal values for the weights and bias? The answer is a method called maximum likelihood estimation, or MLE. The idea is simple. We want to find the parameters that make the model's predictions look as much like the real data as possible. We start with random guesses and keep adjusting the weights and bias until the model's predictions are as accurate as they can be for the entire dataset. Thankfully, we don't have to implement this complex optimization from scratch. For small data sets, you can even use Excel Solver. For more serious work, Python is the go-to language. The scikit-learn library provides a fantastic logistic regression implementation out of the box. And for the most advanced, large-scale applications, deep learning frameworks like PyTorch are the standard. So, to wrap up, logistic regression is a fundamental and incredibly useful model. It takes multiple pieces of information about a student, combines them in a weighted fashion, and uses a simple mathematical function to output a clear probability. It's not just a tool for knowledge tracing, it's the building block for countless machine learning applications. That's it for our deep dive into logistic regression. I hope this explanation was clear and helpful. Now, I'd love to hear from you. Do you have any questions about the model, the calculation, or its applications? Please leave them in the comments section below. Thank you for watching, and I'll see you in the next video.